Good afternoon. My name is Tom Sawinski. I'm a program manager in the Department of Energy's Office of Nuclear Energy. Today I'll be presenting on the Nuclear Energy University program's RC3 area, which is Liquid Metal Cooled Fast Reactor Technology Develop and Demonstration Support Deployment. As you can see from this introductory slide, I am the federal point of contact on this area, and our technical point of contact is Chris Grandy out of Argonne National Laboratory. So again, I'd just like to go over the mission objectives of the Fast Reactor Program and the Office of Nuclear Energy. The overall mission is to perform targeted research and to create sustained testing infrastructure to support the demonstration of U.S. fast reactor technologies and to enable their subsequent commercial deployment. To meet this mission, we have three objectives. The first is focused on research, development, and demonstration of innovative cost reduction and performance enhancing technologies. The next is developing and sustaining a flexible domestic infrastructure and knowledge base for the research, development, and demonstration of fast reactor systems. And finally, to clarify fast reactor licensing frameworks and to develop a science-based approach for regulatory compliance for fast reactor regulatory issues. To meet these objectives, our program has several major R&D areas. Overall, for the commercial deployment of fast reactors, key stakeholders have identified two recurring challenges. The first is capital investment in fast reactors is a dominant cost. Cost reduction will be vital for fast reactor competitiveness. Secondly, a pathway must be established for non-light water reactor licensing, including fast reactors. To address these challenges, the program utilizes input from a variety of stakeholders, such as the industry-led Fast Reactor Technology Working Group, universities, and other commercial entities, to prioritize its R&D in several areas, such as preserving, streamlining access to, and qualifying legacy DOE fast reactor R&D and operational data for use in industry design and licensing cases. These next 2 points are very relevant to the scope this year, and that's why they are highlighted in red. And they are researching more effective fast reactor primary component, sensor, and reliability monitoring technology options that have been identified as leading issues by fast reactor designers. Also operating the mechanisms engineering test loop, which will be the focus of this call, to demonstrate innovative fast reactor components and instrumentation in a prototypic and sodium environment. Following up, we continue to benchmark and improve fast reactor design and safety analysis code suites, and we also focus on qualifying future advanced structural materials through the ASME process for fast reactor applications. So now we're going to go on to this year's scope in the RC3 category. This year, we are seeking proposals to develop experiments, instrumentations, control strategies, and performance-enhancing technologies for the mechanisms engineering test loop facility at Argonne that have the possibility and potential to subsequently be deployed in U.S. liquid metal fast reactor concepts. To give you a brief overview of the mechanisms engineering test loop, it is a prototypic sodium environment test loop located at the Argonne National Laboratory. It contains approximately 750 gallons of reactor-grade sodium, maintained at prototypic reactor temperatures of up to 650 degrees Celsius. In its current configuration, it has 4 test vessels, 2 28-inch and 2 18-inch test vessels, with room for 4 additional testing loops. There's over 300 heater zones and 1,000 sensors, and currently 2 operational tanks with ports for experiments for outside user use. And it includes sodium purification and contamination monitoring. It's a very versatile facility. With that background information, I will now outline some potential areas of benefit under this scope. Overall, we're looking for enhancements to technologies and possible experimental work that can lead to potentially significant benefits in reducing reactor capital or operating costs. Some examples of these areas, first overall, is the development of test articles for metal facility. These test articles can be used to demonstrate a variety of innovative subcomponents for fast reactors or to validate key fast reactor behaviors under prototypic and sodium conditions. Another area of interest is enhancement of advanced sensors and instrumentations focused on what would be needed to operate in a primary liquid metal coolant environment for fast reactors. These include areas such as leak detection, sodium impurity measurements, and various methodologies for level measurement within a liquid metal environment. Next is looking at component testing for innovative liquid metal cooled reactors, self-actuated control and shutdown systems. Some examples include carry point magnet systems and fusible linkage usage. Also experiments for in-service repair technologies, which include visualization sensors for immersed coolant applications, and also technologies to assist for welding and repair of structures that are in contact with primary liquid metal coolants. A few more example areas include improving the performance of tools used within the metal facility, such as rugged high temperature resistance heaters, improved sodium leak detections, thermal insulation that can help reduce heat losses, and other monitoring applications. Another area is development of deployable sensors and prognostic techniques for demonstration in metal that can be used to monitor and qualify materials degradation in a liquid metal cooled fast reactor primary environment. Now, while there is a broad application of areas, it should be noted that these proposals, though they're not limited to the work above, applicants should indicate how their proposed work will help support current DOE, National Laboratory, and U.S. nuclear industry liquid metal cooled fast reactor deployment and commercialization R&D initiatives. We are looking predominantly to test and enhance technologies that will be applicable to the nearer term deployment of fast reactors. For further information on the metal facility, I've included a website in this presentation that gives you an update on some of the capabilities that metal currently has. With that, that's the end of my prepared slides, and I'm open to take any questions you all may have on the scope.
Okay, thanks, Tom. We will take questions over the next few minutes. Please use the question box on the bottom of your GoToMeeting application to put any questions forward to Tom. First question, is funding only supported experiments in metal?
That's correct. Experiments within the metal facility or that have a direct application to enhancing the metal facility's capabilities.
We'll keep Tom on the line for about another minute. He will be presenting again later today, so if there are follow-up questions, he can answer questions about this scope later on as well. So we'll hold on for about 30 more seconds and see if we get more questions. Tom, are industrial partners encouraged?
Yes, it would be good to have an industrial partner that would give them a better idea of the needs of the current technology developers for testing requirements. That'd be recommended.
Can we build a metal loop, or do we have to use the existing facilities?
The purpose of this scope is to utilize the existing facilities, but with that being said, there are capabilities utilizing the metal facility to make your own experimental infrastructure that may include small loops or applications like that, utilizing the facilities and the vessels within metal. So.
Would testing of advanced heat exchangers or steam generators be of interest?
This is a very broad application, and if the applicant can link that with a direct industry or research need for near-term deployment of fast reactors, that is within this scope.
Those appear to be all the questions we have. We will take a break until the 2 o'clock hour, where Tom will be discussing microreactor deployment. Until then, please hang on the line. Oh, we have one more question before we go. Would the scope be supportive of passive reactivity device designs?
I believe one of the areas that I showed an example include novel and innovative shutdown techniques. That particular area, once again, with the same caveat, if there can be a direct linkage to industry need and priority, yes, that can be explored within this facility as well.
Okay, we'll break until 2 o'clock for microreactors. Thank you.